welcome here with me our next presenter, Dr. Karl Menzel. He's from E+ Mobilfunk GmbH, and his topic is the E+ off-grid site project, lessons learned from a unique project regarding the use of renewable energy. Thank you very much. Give him a big hand, please.
Thank you for the short introduction. Ladies and gentlemen, welcome here in Hanover. My name is Karsten Menzel. I'm from E+, the mobile operator in Germany. I'm responsible for environmental health and safety, and I will explain something about our autarkic sites. A short introduction from E+. We are the number 3 in the German market and was founded 1993. Since 2002, KPN from the Netherlands are our shareholder, and some key figures are the annual revenues are around about 3 billion. Our EBITDA are around about 1 billion. Now we have over 25 million customers, and we are 5,500 employees. The idea for the project here, and what I explain, is that we have our targets are that we will be the most efficient network in Germany. So we implement all efficient and all profitable measures in the network, and it is important that we will recognize as an environmental aware organization. So we will introduce innovative projects, promoting new technologies, and that is transparent for the shareholders and for stakeholders. So we have the KPIs in future that we will improve our efficiency around about 20% until 2020 in respect to 2009, and we will work CO2 neutral. This is beginning at 2020. Our motivation is that we give innovative technologies a chance and collect experience with green energies. So the idea was that we built autarkic mobile phone sites, and that we can collect experience for the whole network. What was that? My problem? Next slide. Oh, okay, here's the next slide. So we start a project with support from NOW, and the governance funding for fuel cells, batteries, and the belonging infrastructure around about 2.3 billion. And the second point is that we save the connection energy to the electrical grid. These are more than 50,000 euros. And savings for the energy cost for electricity, typical, we pay in Germany 1.22 cent or 2 euros per kilowatt hours. And we will see here that we have an additional plus investment that is near 40%. So it is not, when somebody asks me, do you have a break even for this project? No, we haven't a break even. It is an additional plus investment is needed that we can introduce solar an autarkic site. And the details of the project, we combined wind energy with solar energy and with fuel cells and a battery backup. And the wind turbine is the energy source for 20 hours. The solar power is the energy for the daylight, and fuel cells works when daylight is not enough and when the wind power is not enough, and the batteries are still down. And an important part is the energy management system. You must manage different components from energy sources. And actually we have built 2 sites, 2 are in progress, and so we have 4 sites near in the future that we was built and have in our network. And this is when we look for the correct site place, it must be a completely new site, and it must be an adapted infrastructure for cell power, and we need the technical requirements that the required energy is not over 2.5 kilowatt. So we can install these techniques for the 2G and 3G network, and typical with maximum of 2 microwave links. Yes, here you see that we used different wind turbines. We are used vertical turbines from 2 different manufacturers, and typical ways are 5 to 10 kilowatts in the peak power, and we used solar cells with a peak power from 8 to 12 kilowatts output, and we use a tracker to improve the outcoming in the morning and in the afternoon, so we can manage this better than we have fixed solar panels. And the important part here for this forum is the fuel cell. We have the idea that we use renewable energy, so we don't use diesel aggregates, and we used fuel cells as a backup solution. And here you can see the hydrogen storage rooms here with 2 bottles packages, and we have 2 different solutions. Some is in the container on the left side, and there are the batteries inside the container. And in the other solution we have special boxes for the batteries outside of the container. And we have a simulation of this site. You can check a simulation where you can manage winds, solar and seasons influences, and you can see the output, the energy output of different climatic and weather situations, and you can see what the wind turbine delivers on energy and what the solar panel, and when you need the fuel cell. You find the simulation on the internet site from Clean Power Net, and you can check the simulation and get some experience with our autarkic solution. Now we'll bring you some information about the earnings of the different energy, and in the slide picture in the top you see the expected energy, and the red one is the energy from the wind turbine, the blue one is the energy from the solar panel. In the summer it's higher than in the winter, and the green one is the expected energy from the fuel cell. And bottom you see from two sides the real values. On the left side you can see that the wind turbine is far away from that what we expected. And in the second it's a little bit better, but our experience is that we are a factor 20 under the expected value by the wind turbine. And so we need more full cell energy, and it's our important experience is that the wind turbine doesn't work so well, so we expect it. Here you found the first calculations. In the table in the top you see rails from 4 sides. Number 3 and 4 are not in operation, so we have actual rails from 2 autarkic sites. And you see that the wind turbine have earned 7,500 kilowatt hours. The fuel cell 37,000 and the solar panel 63,000 kilowatt hours. When you calculate the theoretical cost against from the hardware cost, you can see in the table that for the wind turbine we have a kilowatt hour price from 8 euros, more than 8 euros. The full cell energy cost of round about 0.7 euros, and for the solar panel 0.6. On the second side there are a little bit other ways, but you see especially the wind costs are very hard, not acceptable high, and the learning of this project is that we in future will plan this with solar energy, with fuel cell energy, and not with wind energy. But the concept works. We have shown that in a field situation, safety operation is possible. We have managed the service, and we have a stable operation, and the logistic for hydrogen works in Germany very well, so we can say it works, and we have since more than 12 months a good experience with this autarkic sites. Yeah, thank you for your kind attention.
Thank you for this informative presentation. I think this is your applause here right now. Yeah. Thank you, Dr. Menzel, for being here. So I'm really sorry, but we have to continue directly. So if you have any question, I think you will stay here at the technical forum right here in the back. So if you have any question, please come to him directly and ask your questions. So we will continue right now with our new topic. Batteries, the right solution for fuel cell startup and load fluctuation buffering. And it will be held by Christian Stampfer von HOPPECKE Batterien GmbH. Here we go.
Thank you.
Thank you.
Thank you very much. Yeah, welcome. My name is Christian Stampfer. As already said, I'm working for HOPPECKE Batteries. We as well have the, let's say, the opportunity to add to our battery portfolio as well fuel cells, which we are buying in from Relium from the States, and we have here already established a couple of projects where we combine batteries with fuel cells. So the content of the presentation, fuel cells, where we use them normally in our field, and then why battery storage of energy is, from our point of view, as well needed. And then the last topic is the advantages of batteries in combination with the fuel cells, because you have then at the end of the day more options to, let's say, set the right parameters for your complete system. In our field, we see that we use fuel cells in our portfolio and also in our, let's say, field for the small applications. We have very small off-grid applications, lighting, in some areas the control of pressure sensors on, let's say, the gas pipelines in Russia. We have as well applications for larger off-grids. These are the critical communication sites, for example, in Norway, as seen here on the picture, or like the application Mr. Menzel just explained, where two of the sites are also planned to be installed with our solution. So these are these typical off-grid applications. And the third, and from our point of view at the moment, biggest opportunity for fuel cells are the backup systems. So the very long backup for on-grid stuff. This is similar to the presentation of Mr. Oswald, who explained this for the BOSNet, where we are also having one part of the lots where our fuel cells together with the batteries are installed. So what is the main, from our point of view, the main reason why an additional energy storage is needed in combination with a fuel cell? It's very often the fuel cell itself, because depending on the load of the fuel cell, the open stack voltage can vary. So, and depending here how sensitive your application is, you need an additional source of energy to stabilize this kind of output, so that the load of the customer, of the application, is supplied safely. And batteries, of course, are here a very good medium, because you could scale them to the need of the application, and you have here also a very well established and proven energy source for supplying DC current into the applications. The other point is, depending on the let's say dynamic of the load, in some cases a fuel cell can run into an overload situation, and there the battery is let's say the perfect, let's say, backup of the fuel cells to let's say shapen the peaks of the loads, so that everything is at the end of the day then a little bit more, let's say, smooth in the operation for the fuel cell. What are the additional advantages and reasons for using batteries? As you know, and then a lot of people here in this auditorium are working for fuel cells, fuel cells take a couple of minutes before they are at full load. Depending on the different technologies, these are hours up to a couple of minutes, but the load, the application itself, with a shortage of energy, needs the energy right now, just at the same second as you have the blackout. And therefore the battery could help and buffer the first couple of minutes. It is very easy and very well approved how to size the battery, and depending on the load, depending on the energy you need, you can add big or smaller batteries in parallel to the fuel cell. So from our vendor, we have a kind of a guideline that approximately a good value would be just about 20 ampere hours battery backup per 1 kilowatt DC load you have to supply via your fuel cell. This gives you enough security that your load will be covered by the battery for the startup time, and it gives you as well enough security that when the fuel cell starts and it's maybe need a restart, that you still have back energy due to the battery, and that means you have the possibility to start more than once if this is needed. The other time is hydrogen is still, let's say, an expensive source of energy. In some countries, it is even the distribution of hydrogen not so well adapted, and with a good sizing of a battery, you could play with the starting point of the fuel cell. That means if you have shortages, energy shortages, blackouts, you could then define that the first couple of minutes or maybe even the first hour would be served by the battery, and only if you really have very long blackouts that then the fuel cell starts to run. This will help you to reduce the energy supply via the hydrogen. The other point is that you could also set in the, let's say, settings of a fuel cell, that the fuel cell, for example, not only starts when the electronic devices, the monitoring sees there's a blackout, you could also trigger the fuel cells by the voltage level of the battery. So it means you could drive the battery down, and then when the fuel cells detect that the battery voltage is at a certain level, and then the fuel cell can start. Also this helps in the different application to reduce the number of startups and to reduce the hydrogen consumption of the fuel cell itself. Together with other sources of energy, like Dr. Menzel explained, batteries with fuel cells, with wind, with solar are a perfect combination to generate off-grid applications where you then have a 24 hours, 7 days per week energy supply even without any grid. And the battery in this point is playing a major role because they can store all this energy which is available from wind and solar, and they then also are able to cover, let's say, the little peaks and starting issues with the fuel cell. So therefore, also here in combination with fuel cell, the battery is a perfect match. One other point where we already have, let's say, designed and engineered a combination between fuel cell and battery is in very remote areas, that with a battery and a fuel cell you could generate a kind of a cycling mode, so that for a couple of hours or even up to days the battery is supplying the load, the application, and when the battery voltage level reaches a certain value, the fuel cell starts, take over the supply of the load and charging the battery back, and therefore you can do this charging mode, and with this cycling mode. And with the cycling mode, you could help as well to reduce the fuel consumption, which in some areas is really an issue, because you have maybe to travel a couple of hundreds of kilometers to the different sites where this fuel cell is running, and to refill fuel like propane gas or methanol or hydrogen. And here it's a very important point that the consumption of this fuel is to be reduced. And with cycling, this is a point to do it. So, the summary. So from our point of view, fuel cell and battery are not working against each other. It's, from our point of view, always a great combination. They support each other, and I think together they bring definitely a lot of advantages for a lot of different applications, off-grid and on-grid. Thank you for your attention. If there are any questions, I will be there on our booth, and we are then very open to explain different battery technologies and the working together with the fuel cells. Thank you very much.
Thank you very much. So it's your applause. Maybe you can stay for some minutes here at the technical forum, though can somebody come directly to you with the, if he or she has some questions. So we continue directly with our last report here in this session. It's dealing with reformed methanol backup power system, and the company who belongs to is Serenergy, and he is at the group exhibit Hydrogen Fuel Cells and Batteries here. And please give him a big hand, Mr. Friis Jensen.
Thank you very much. I'm going to talk a little bit about something else, reformed methanol fuel cells. I'm representing Serenergy and Fischer Eco Solutions here today. It's a partnership in bringing reformed methanol fuel cell systems to market. We focus on high temperature PEM fuel cells integrated with methanol reformers. We focus on from a few hundred watts and up to 5 kilowatt systems. They are based on a modular platform, so they can be integrated into various kinds of systems, cabinets, and so on. The HT-PEM technology has some characteristics that has advantages and disadvantages. There's a high operating temperature of 160 degrees, which enables or demands a startup time that's a little bit more than a few seconds. It's from 5 minutes to 30 minutes. It has a high operating temperature, which makes it easy to cool. And on the other side, it makes it relatively easy to have systems operating at high temperatures. There are no water regeneration in the systems or humidifications, which makes for a simple system, but that's fuel cell related. In the 200 watt to 10 kilowatt range is where we operate with systems, either as separate systems or modular systems. Today we focus on markets with a 5,000 hour lifetime operation span, and we have a increased focus on an integrated and a compact system design that enables a easy integration into existing and new telecommunications networks. The system core is made out of a HT-PEM stack, which is here, and a methanol reformer that is tightly integrated into the stack. One of the tricks with the methanol fuel cell technology with HT-PEM is you can reuse the high waste heat from the fuel cell to actually drive the reforming process, or at least the fuel evaporation process. So this enables a relatively high electrical efficiency, which I will get back to later. I'm not going into details, but there's some nice arrows you can look at later. So this transforms into a core product, which I will go a little bit more deeper into detail with, a 5 kilowatt modular block, 75 kilograms. Dimensions, it fits in a 19-inch rack, which is pretty much what is needed. It has a weight of roughly 75 kilograms. It has all DC-DC steps integrated and has an output voltage of 48 volts. So this is basically all you need. And on top of this, you need a battery system, as discussed before with HOPPECKE. And you also need a fuel system, which I'll get back to in a little bit. The efficiency, as discussed earlier, on a combined high-temperature PEM and methanol reformer system is relatively high. At 5,000 watts, you see an electrical efficiency of around about 40%. And if you do half load, you get a little closer to 45%. So with these two technologies combined, you get a electrical efficiency that is comparable to that of a hydrogen-based fuel cell system. And that's one of the key points. The way we have designed the system is that you have the module itself here, and the batteries and the fuel tank, as well as the enclosure around it, can be completely scalable. So it can be any type of battery, lead acid or lithium ion. The fuel tank, which is supposed to hold the methanol, can also be scaled from 20 liters up to 1,000 liters if needed. And the last thing is, if you have some need for excess heat from the system, you can extract that from the system, or else you can just dissipate it into the open. So that's the philosophy, that the minimum viable concept is in our box, and everything around it can be scaled to fit any need. Methanol, we operate with a 60% methanol and 40% water mix of the methanol to feed our steam reformer, which is the technology we use. Here's an example of a 20-liter cartridge. It can also be a 1,000-liter cartridge. It doesn't really matter. It's a PE canister, so it's non-pressurized and very simple liquid. To accommodate with the toxicity of methanol, we use no-spill solutions. So this means no matter what you do, you will always be sure to have the user or the operator away from the fuel. I won't go too much into detail about methanol, but that's the fuel. One deployment example here is a 2 times 350 watt system integrated into an existing telecommunication site. So this means the on-site battery pack is basically just integrated with a fuel cell system standing on the side of the unit, built into a generic type cabinet with 3 canisters of 20 liters fuel, which supplies 72 hours autonomy if needed. It's simple to set up. It's no zoning in you can say in terms of legislation wise, and it's a very simple way to upgrade the backup power capacity from 4 hours in the battery pack and up to 72 hours. Very quickly in summation, what we focus on is a tightly compact system that has a high electrical efficiency. It's simple, there's a very low maintenance, and we have a high modularity. This means that if you're looking at the 5 kilowatt system, we can basically scale the output power based on the stack. So if you need less power, we can actually hit the exact rating needed. And the derived benefits of that is we have a very simple fuel logistics. As discussed before, fuel logistics can sometimes be tricky. That's not the case with methanol. The fuel cell size and basically how you integrate it is also a very simple thing to do with the methanol systems. And if you have any questions or need more information, we're just on the other side of the booth, and that's where we are.